And welcome to today's Cosmology segment. This one is beyond interesting, and we've got a whole lot of information shoved into this one. We decided to stream it live to Twitch, by the way, twitch.tv/smAsho. Thanks to our new followers over there. And if you follow us on Twitch but not YouTube, what are you waiting for? YouTube has most of our content, youtube.com/smAsho. Highly recommended that you check out our playlists, as the Cosmology segments are pushing 200 videos. Also, check out our weekly smAsho Stream Any chats. We'll be streaming another one today, as well as making another video in the series of The Diamond Anvil Too Hard to Smash. So check our playlists for sure. We're also on BitChute. Recently put an exclusive there. If you want to see our Discord channel, check that out. You can find a permanent invite to it right on our homepage. So right there, smAshomash.com, smAshomash.org will redirect you to this page. Push the arrow to see our social media links. The merch shop, the forum, and the other stores are available right there on the homepage, smAshomash.com. Welcome to the Neo-Renaissance. One of the places to follow us would be on Instagram. And there is a convenient link for you there as well. Instagram.com/smAshomash is the URL. And check out our merch shop as well. Thanks to everybody who picked up merch. So our Cosmology segment is absolutely fascinating today. Multiple insane stories. Let's get to it. So first of all, we're going to start out with an article about a teardrop-shaped star. It's the only known fast radio burst repeater ever discovered, and it's only about 1,500 light years away. It consists of a very massive hot star and a less massive hot star. With a periodicity, the orbital period of this system is only about 100 minutes. Let's talk about it. This teardrop-shaped star, believed by mainstream astronomers to be the predecessor to a supernova. However, the article will refute these theories if you know what you're reading. So, the massive binary is known as HD 265435, the only known fast radio burst repeater. It features a teardrop-shaped star, which is extremely distorted because of interaction with its neighbor. So this is believed to be soon to go supernova. And when we say soon, we mean in like 30 million years. We're talking not even geologic timescales. We're talking astronomical timescales. Anyway, that star orbits the other star at a rate of about 100 minutes. Now, white dwarfs are believed to be, quote, dead stars that have burned out all their fuel and collapsed in on themselves, making small but extremely dense stars. And some of us don't believe that that's the way stellar evolution works. But in any case, the observations are the observations. So let's just stick to those, as there really isn't any argument about what kind of emission spectra we're getting from these type of objects. I'm just letting the article slowly scroll here. You'll find links to the paper associated with this article at the bottom of the SciTech Daily article here. Anyway, the hot subdwarf is believed to be about 0.6 stellar masses. And they're going to talk about all kinds of things like gravitational waves. Let me read a quote. Type 1a supernovae are important for cosmology as, quote, standard candles. Their brightness is constant and of a specific type of light, which means astronomers can compare what luminosity they should be with what we observe on Earth. And from that work out how distant they are with a good degree of accuracy. That is a run-on sentence. By observing supernovae in distant galaxies, astronomers combine what they know of how fast this galaxy is moving with our distance from the supernova and calculate the expansion of the universe. All right, I'm going to leave that there and let the article scroll the rest of the way. So this is additional studies here on this only known fast radio burst source. And hey, I don't blame them. It's an interesting X-ray binary, to say the least. And it's pretty close to us, relatively speaking, in the Milky Way galaxy. It could actually affect things on Earth. So anyway, here it is on Pan-STARRS. That is the Pan-STARRS optical bands. And you can see the oblong shape of this, eliciting the fact that there are two objects there. And let's take a look at it on the 2-mass. So that was optical light, bands Z and G. Here's infrared light from the 2-mass. Great view of that oddly shaped X-ray binary system. And here it is in blue light, looking a little bit more symmetrical in that wavelength. So that is HD 265435. And let's put up the optical bands once again to close out this section of the cosmology segment. By the way, we're wishing Chrome Dome Jeff Bezos good luck when he enters space, as I don't want to breathe in Jeff Bezos, and I'm sure you probably don't either. We're hoping Jeff Bezos all the success in his space travel endeavors. Blue Origin gets the okay to send him and 3 others into space. And unlike Richard Branson, he's expecting to actually go to space, as Branson kind of only made it to about 66 miles. Only about 53.5 miles, actually. Anyway, best of luck to Chrome Dome Jeff Bezos. Today we picked a random number. It came up to be 166, which is a quasar, PKS 0516-621. It's number 166 on the Neil Gorell Swift Bat X-ray Observatory. There are the outputs of that. That's the hard X-ray spectra of this quasar. Number 166 on the Neil Gorell Swift Bat X-ray Observatory. And here's this quasar, known as B0516-621. That is the quasar in infrared spectra from the 2-mass. And let's see if it shows up here in ultraviolet. There it is in ultraviolet. And look how dim it is in ultraviolet. Very dim, distant quasar there. And we'll take a look at it here on the DSS2 in blue, very dim in blue as well. And I don't think this one shows up on Pan-STARRS at all. Let's move on. I'll put the 2-mass back up for you. There's that quasar, an active galactic nucleus with the galactic jet oriented directly toward you and me. Did you know that gamma ray bursts were predicted as they're showing up in a schedule? Yeah. It's true, folks. It's true. Why? Because of a magnetar near the galactic core. So they can emit bursts of gamma rays. And this is another article that you will find refutations of the theories that drive how these things work. So I'm not going to really comment too much on this one, other than the fact that there's a periodicity that is not explained by the standard concordance model of physics. How are these things doing what they do? If the tidal disruption events cause stars to be destroyed, then why do we still see stars at the source of the tidal disruption events? I'm not even going to get started talking about gravitational waves and the problems with that, quote, science, end quote. But in any case, we're just letting this article scroll here, as there seems to be some predictability in the gamma ray bursting activity from this particular magnetar, known as SGR 1935 plus 2154 from the constellation Sagittarius. And you can see it goes through times of activity and inactivity, although it doesn't show up in all the active windows for some reason. It's not understood the mechanism. This article from phys.org, titled Gamma Ray Bursts Predicted Last Year Show Up on Schedule. So kudos to those who forecasted the gamma ray bursts. Today's astronomy picture of the day is a simulation of a black hole merging with a neutron star, and this is a bunch of cartoonish silliness as far as I'm concerned. This is believed to be gravitational wave 200115 detected in January 2020 from LIGO and Virgo observatories. And what this is an alleged signal from laser interferometry on the ground coinciding with some sort of an event in the sky. And I'm not even going to talk about the way they look for this stuff, as I don't think it's science. Now, here is some science, and this is pretty important stuff here, folks. Now we're talking about tree rings showing extreme solar events. Why? Well, because it's got to do with isotopic ratios. Trees, they take up isotopes, and the number of radioactive isotopes to normal isotopes in ratio give us insight into what was going on. So we're talking about carbon-14 versus carbon-12 isotopic ratios here. And anyway, long story short, it gives us insight into extreme events. So let me just make sure the stream is going good here. Stream looks just fine. Let's continue on. Anyway, turns out there was an extreme event between 5,411 and 5,410 BC. So there was an increase in atmospheric carbon-14 by 0.6% over the northern hemisphere for that period. So this is pretty important, and measuring tree rings to get the carbon-14 ratios out of them gives us insight. Additional confirmation needs to be made about measurements of beryllium and chlorine to figure out if it's caused by a supernova or by something a little bit more local, like activity from El Sol. In any case, you can find the paper if you search for a single-year cosmic ray event at 5410 BCE registered carbon-14 of tree rings. So the full article is there in the Geophysical Research Letters. Perhaps check that out. Another fascinating article. And let's talk about the solar wind. So since the mechanism behind the sun, in my opinion, is not understood, how stars do what they do. The sun is the Rosetta Stone of all cosmology. Let's go a brief timeline here about how things were understood. So Kepler realized that there's probably wind going on in space because of comet tails. In 1842, Francis Baily came up with the idea that perhaps the sun has an atmosphere, as he saw it during a solar eclipse. What about the coronal heating problem? Why is the corona so hot? What about a new heating problem? A new heating mechanism, rather. Hannes Alfvén proposes the existence of a new kind of wave forming in electrically conducting fluids. Is the solar wind made of particles? That was a hypothesis by Kepler in 1943. What about Eugene Parker, for whom the Parker Solar Probe is named, back in 1958? Right as we saw the sun go into the highest activity state of the modern era in 1959, solar wind was detected in that year. And then a detection of slow and fast wind by NASA's Mariner 2. What about coronal holes? We didn't even know about coronal holes until the 90s. But we were discovering fast solar wind from them. By 1973, nanoflares. Talked about in 1988, once again by Eugene Parker. What about Ulysses, which flew over the sun's poles and showed us enduring holes, coronal ones, in the sun's poles around times of solar minimum? Slow solar wind and heat streamers, 1995, and the Parker Solar Probe launch in 2018. Why? A very important article here, talking about the electrical field associated with the surface of the sun. So, nobody is refuting the idea that there is electrical stuff going on the surface of the sun. Here's a diagram. And what happened here is the Parker Solar Probe got within to only 9 million miles from the sun, and it was able to measure the difference between trapped electrons and escaping electrons, which gives us insight into the electrical potential and field and so on of the coronal region. Now, while we've got great disagreements here regarding how it is that all those electrons are there, where they come from, and so on, this is important as it is another step in understanding by the mainstream how stars work. Now, soon we're going to write a paper on the mechanisms that drive the solar polar field reversal cycles, sunspot cycles, etc. But this is super important, as, quote, the sun's electric field arises from the interaction of protons and electrons generated when hydrogen atoms are stripped apart in the intense heat generated by fusion deep within the sun. Now, of course, that mechanism I don't agree with, but in this environment, electrons with masses 1/1800th that of protons, in other words, 1,800 times less, which is a terrible way to explain the proportional size of something. Electrons have a mass of 1/1800th of the mass of a proton. It takes 1,800 protons. It takes 1,800 electrons to equal the mass of a proton. Anyway, blown outward, less constrained by gravity than their weightier proton siblings. But the protons with their positive charge exert some control, reining in some electrons due to familiar attraction forces of oppositely charged particles. So I'm just going to let the rest of this article stream here and scroll here. Feel free to pause the video. Another super important article. A telltale sign of the sun's electric potential. And we're getting the data thanks to the Parker Solar Probe. So fantastic there. Just fantastic. Measurements of the sun's electric field. Does it mean stars are electric? Well, certainly not. At least not intrinsically. And just to clarify, we've never refuted the fact that there are electrical things happening on the surface of the sun, the surface of the earth, and so on. We just don't believe that everything's connected, that everything's electric, that stars are fundamentally electric, and so on. And that's today's Cosmology segment. I've been your host, Dan, a.k.a. smAsho, signing off from the Smash News Network. Least busted, name in news.